Hi guys, season's greeting on German's MATLAB coding. I came back with another clip which discusses how one can graph Nyquist plot of a control system in MATLAB. Viewers need the background for transfer function entering, which we addressed in clips 36 and 37. 36 addresses transfer function entering from polynomial coefficients, and 37 addresses transfer function entering from zero pole gain information. To implement Nyquist plot, we need the embedded function Nyquist, which has the syntax Nyquist, input argument of which is transfer function of the control system. Let us talk about the theoretical context of the Nyquist plot. We know that any control system is represented by G of S when parameter S is replaced by j omega. Then frequency function g of j omega has four components, namely magnitude, phase, real, and imaginary parts. Nyquist plot basically the graph of imaginary part against real part. The graph also traces a polar curve. The magnitude of frequency function becomes the radius vector of the polar curve, and phase angle of the frequency response becomes the angle of the polar curve. The omega or angular frequency theoretically changes from negative infinity to positive infinity. Accordingly, the phase angle changes from 0 to 360 degrees. Let us go through example 1. We would like to obtain the Nyquist plot of control system G of S equals S plus 4 over S square plus 4S plus 3. Enter the given transfer function using numerator and denominator coefficients, which are 1, 4 and 1, 4, 3 respectively. Use TF to enter the transfer function and assign to workspace variable G. In the next command line, call the Nyquist with G as the input argument. With the execution of the last statement, you must see the figure response from MATLAB like the screen. Here, the horizontal axis or real axis basically the real part of the frequency function g of j omega, and the vertical axis or imaginary axis basically imaginary part of the frequency function g of j omega. The curve is a closed one. Accordingly, frequency changes from minus infinity to plus infinity, but that information is hidden here. And phase angle of g j omega changes from 0 to 360 degree. In example 2, we have a third order system which is given by g of s equals s square plus s plus 4 over 2s cube plus 2s square plus 4s plus 3. We would like to see the Nyquist plot of this control system. Here the polynomial coefficients are 114 and 2243 for numerator and denominator respectively, and enter them by using TF and assign to workspace variable G as shown on the screen. In the next command line of MATLAB, call the G as input argument of Nyquist. This execution also brings about the Nyquist plot as seen on the screen. Once again, the real axis is the real part of frequency function and imaginary axis is the imaginary part of the frequency function. The curve is a closed one as you see, and omega changes from minus infinity to plus infinity, and phase angle of the frequency function changes from 0 to 360 degrees. Alright, we would like to terminate our session here. Do share, like and subscribe our contents. I hope to see you in next clip. Bye for today. Stay safe and take care.